컨퍼런스에서 베스트 페이퍼 어워드를 여러 차례 수상하셨고 그런 식으로 이제 연구 업적도 많이 인정을 받으셨습니다. 그래서 일단 제가 동영상 파일을 공유를 해서 진행을 하겠습니다.
Hi everyone, my name is Gino. Today I'm going to talk about social robot navigation. So before I start, let me introduce my research team, Bot Intelligence Group at Carnegie Mellon University. And in our group, our focus is on roughly on 4 different things.
갑자기 오디오가 안 나오는 것 같은데요. 저만 그런가요?
예, 조교님, 저도 오디오가 안 나오고 있습니다.
Generally for the human robot collaboration, our research is more focused on the participatory presence for controlling multiple robots in the
다시 들리시나요 지금?
예, 지금 들립니다. 양 교수님께서 하신 거군요. 예, 지금
다시
들립니다.
제가 좀 뒤로
조금 앞쪽으로 해주십시오. 감사합니다.
시작하겠습니다.
Our focus is on roughly on 4 different things. So the first topic is how to make robots navigate in a dynamic environment, which is today's topic, social robot navigation. And then the other end of this planning problem is how to use semantic understanding, including visual perception and language understanding for the robot's planning. Generally for the human robot collaboration, our research is more focused on the participatory presence for controlling multiple robots in a remote location. And then the last topic is creative AI. So this is how we are going to use machine learning and AI and robotics technologies to facilitate human creativity. So for instance, how to generate creative paintings. So a quick overview of the topic is I'm going to go over the problem definition first, and then a list of challenges within this problem domain using some of the existing approaches as examples, and then suggest some future interventions. First, let's look at what a navigation problem in a real world would look like. So in this example, if you look at it in this environment, we see a lot of static obstacles. The examples of static obstacles here are poles, some buildings, with stands, and so on. And then there is also dynamic obstacles. So these are obstacles that are also moving. So here there are many different types of dynamic obstacles, including pedestrians, bikers, cyclists, vehicles. And then if we look at this scene a little bit longer time, then we realize that there is also invisible lanes. So there are man-made rules that are not visually available to the agents, but we kind of learn from other members of this social context to behave. So this includes something like the traffic rules or more general social norms. So this navigation in the real world is a very difficult problem. So to design an algorithm for solving this navigation problem, we formulate the problem in a kind of compact way. So the general navigation problem is defined in such a way. So given a destination or a goal, the problem is to find a sequence of actions to move from the robot's or the agent's initial state or the current state to reach the goal. And usually there is some objectives that are associated with this general problem solving. So the objective is to either minimizing the cost or maximizing the reward with respect to different types of objectives. So the first one, the most general one for autonomous navigation is obviously reaching the goal. So how fast can you reach the goal, or what is the shortest path to the goal, and so on. And then the second one is the safety. So the important thing is the robot needs to navigate to the goal, but if it crashes the vehicle, then it's not an acceptable solution. So these are usually hard constraints to avoid avoid a collision. And then so these are the more classical navigation objectives. And then the additional ones that are relatively newer concepts are kind of including this concept of comfort, which is a little bit more than safety. So an example for comfort is if the robot or the vehicle kind of avoids a collision with a very, very small margin, that is still considered safe because there was no collision, but it creates discomfort. So you feel risky or unsafe around that robot. And then the last one is naturalness. So this is just for the human users. So humans do not want to be disturbed. Design a robot that is going to operate in a human environment. We'd like to enforce this type of objective in the robot's behavior so that the robot reaches its goal safely and also providing some comfort, but also the behavior looks natural and blending in with the human population. Right? So under this social navigation problem, we can roughly divide the problem into kind of three categories. There are many different ways to divide these groups, but for today's talk, I'm going to use these three categories. So the first one is the general navigation that I just mentioned. So this is usually assumed in a static environment. So the focus here is to find a solution that will get the robot to the goal. And the main objective is to find a path that is most efficient in terms of the cost of driving. So that has a close tie to the traversability. So the general cost has to do with how smooth or how difficult the terrain is for the robot to navigate over. So the environmental context or the physical constraints are, in a way, the major block in this general navigation research. And then the social objective in this case is a collision avoidance. So how to put these, keep the robot safe so that it doesn't crash. And then the second one is a pedestrian prediction. So this second problem is not really a navigation problem. So it is making the prediction for how these agents will behave in the future time steps. So this problem definition generally doesn't even include the goal in the problem definition. So if we use some algorithms for pedestrian prediction for creating agents, then we can generate agent population that kind of moves around like humans, but we cannot really use that to send a robot somewhere because it doesn't include the notion of the goal. Okay? And here, the pedestrian prediction, the social objective is naturalness because it's mostly for human pedestrian prediction, trajectory prediction. And for the environmental context, a lot of existing approach for pedestrian prediction focus on the trajectory only. So that means it assumes a free space. So the environment itself is obstacle-free. So we can say the problem formulation kind of puts all the pedestrians up in the air, so they're kind of floating in the free space. So it's not very realistic, but unfortunately, not many people are working on including both the static and dynamic obstacles. So this is a good area to for future direction to think about. And then finally, social navigation is combining the two together. So how do we do the navigation in a dynamic environment that includes other moving agents, mostly pedestrians, but it can also include the vehicles or cyclists and so on. So since it's a navigation, it still has a strong objective to reach the agent's goal, but it has also as important objective, which is to comply with the social norms or to provide comfort in the population. And also for this problem, similarly to the pedestrian prediction setup, a lot of existing approaches kind of ignore the static environment. So the social navigation algorithm, the formulation is mostly focusing on the trajectory only. So it doesn't include the static context. So this is a part that I'd like to kind of ask people to start looking at how to include these both static and dynamic obstacles into the problem. Okay, so I'm going to first look at the pedestrian prediction problem, and this is not a navigation algorithm, but it's still useful. So there has been a lot of existing work recently for the pedestrian prediction part. So the examples I put here are already kind of outdated, and there is a survey article that gives a very nice overview of this field. So as I mentioned, this is a prediction and not a planning algorithm. But why do we even study these prediction algorithms when we talk about social navigation, which is a slightly different problem? Because these ideas that were developed for pedestrian prediction includes a lot of good ideas for modeling the interaction among the agents. So, okay. So I'm going to use social attention as an example to illustrate this pedestrian prediction problems and how this can be modeled. So social attention was an algorithm proposed by Univ, one of my former students. And the assumption here was people attend to maybe not everyone in the environment when we navigate in a crowd, but it's a small subset of the other agents, but it may not be the closest neighbor. So it may be someone that is far away, but running towards, for instance. And the approaches before this sort of attention was really focusing on the immediate neighbors to scale the algorithm. So we start with this assumption that maybe it's a small subset, but not the nearest neighbors. So, okay. So let's look at how we computationally model this social navigation or the trajectory prediction problem. So in this example, we see four people, and this is at a fixed time step t. So we see these edges represent the spatial relationship. So at a fixed time step, they are all in different locations, but we can see kind of relative position of each agents to each other. So this is a spatial relation at a fixed time step. And then if we do like one rollover over the time step, then after one time step, all the agents may be in a different position. Maybe they stay in the same position as well, but the position at time step t and another position at time step t+1, between those two, there's a temporal relations. So these are the kind of the illustration of how we might be able to model this in a computational way. Okay, so the idea of a spatial temporal dynamic graphs, this is a classical representation that's been used a lot. So because a lot of data includes spatial relationships as well as the temporal relationships. So in this case, using the same example before, instead of 4, in this example, we have only 3 pedestrians. So each pedestrian, we will create a node. So for each pedestrian is represented as a node. And then the edges represent the relations. So at a fixed time step, we can see there is a relationship between each pair of agents in this environment. And then this green arrow represents the temporal relations, because the same agent may be at a different position and in the different time step. So if you unroll this compact representation, we will see a very similar representation that we saw in the illustrative example. So here, so again, the node represents each agent, and then these green arrows represent the temporal dynamics over time. And then these blue edges represent the spatial interactions between, in this case, human and human interaction, but we generally say a spatial relation or spatial interaction between agents. So this is a kind of compact representation of the trajectory data. And now we want to kind of implement this idea. So there are many different ways to implement this spatial temporal data. And these days, everyone does this deep learning. So we will look at some of the options. And since the trajectories are sequential data, many people thought that maybe RNN is more appropriate because it's a structured sequence. So, right. So using an RNN, very abstract view, the way it works is in RNN, the output is computed using the current input and the previous output. So we will use this idea to first try implementing these spatial temporal graph. And luckily, someone has already tried a similar approach. So this structural RNN is a RNN implementation of the spatial temporal graph. And in this original paper, what they did was using this structural RNN to represent how people interact with objects. So like if I pick up a ball and move it to somewhere else, like how to represent those in a kind of computational graph. So it is a similar but slightly different problem. So what Anirudh did was using kind of similar structure and then turn that into a trajectory prediction model. So in this case, the novel idea here was, so all these agents are represented as a kind of a RNN node. So all the agent nodes are the nodes, and also the edges that's representing the spatial interaction and also temporal interaction. They also are represented as a kind of separate RNN. So, and in order to compute the social interaction part, which is kind of when I make a decision, when I'm kind of walking in a crowd, there are like other agents. So how these other agents moves or the trajectories will affect my decision making. So this is the part that's kind of summarizing the social impact. And as I mentioned, the previous approaches had a kind of struggle to represent this part, because if you include too many agents, then it doesn't scale very well. So the proposed idea before was using a social grid, which is kind of looking at the close neighbors only to limit the number of neighbors in this case. And what Anirudh did was using the attention model to solve this scalability issue. So let's look at what the attention mechanisms are. So maybe some of you are already familiar with the attention mechanism because it's so popular, but it is a kind of a way to reorganize the input in a kind of like a structured way. So, okay. So very quickly, so the attention mechanism is another structured representation of the input. And then, for instance, it can be represented as a fixed size vector called the context. And then the idea is to learn another function that can put the weights on this context vector so that you can weight differently, like where to put your attention more. So I'm not going to go into too much detail on this, but you can see this is another function that's including the context here, and alpha here are the weights. So the learning algorithm will train the weights so that it can learn the weights for which part to put more attention to. There are two different ways to use this attention mechanism. And for the like the most general case, the social soft attention, which is using softmax, makes sense because it's differentiable. But if you want to use a hard attention, sometimes it works better, but then you might want to use a sampling. Okay, so how do we use this attention module idea in the trajectory prediction, especially for modeling this social interaction part? So since there can be many agents, the attention module can turn that into a fixed size vector so that the algorithm is more scalable. Okay. So the results back then, it was the state of the art according to kind of popular metrics that were used. And these are just showing some kind of qualitative results. So in this example, it shows like when you're far away from the crowd, kind of try to put, it's kind of hedging the bets. So you don't know who is going to come near you. So put kind of similar weights. And in this example, it's showing even if this green agent is the closest, it doesn't, the agent doesn't really pay too much attention to this one because it's not really moving. So rather putting more attention to these farther away agents because they're moving. Okay. So that was the idea of using an RNN to represent this spatial temporal data, something like a trajectories. And more recent approaches was the general limitation of an RNN is if the prediction length is getting longer, then the RNN tends to get noisier. So some people have thought about what about just using the CNN. So in the CNN case, you can still use the input and then just slide the window in a one-dimensional fashion. Okay, so Eagle, again, one of my students came up with this new algorithm called STEC. So he also has the same intuition. So CNN probably is a better performer for the long-term prediction. So like the short summary was a spec. Again, it hit the newer state of the art, but I'm going to kind of address what are the evaluation challenges. But before I do that, let me first introduce the algorithm a little bit. Maybe not into too detail, but a little bit. So the intuition is the motions are affected by other people's motions, and then there exists some similar motions that trigger similar reactions. So it's kind of very intuitive idea, and in fact, this similar idea has been used a lot in other kind of problem domains like computer vision, where they use kind of detected patterns, something like anchor box, to locate the bounding boxes slightly better. So in this space, motion patterns are kind of a rough match. So it doesn't have to be the exact match, but generally, if the pattern matches, we can reuse those patterns to predict the reaction of other agents. Okay? So this is an illustrative example how we might be using these motion patterns to represent the trajectory. So suppose we trained all these nice motion patterns from data. So these gray arrows are the learned motion patterns. Then by observing these green trajectories, can we represent these green trajectories using these patterns? So these numbers kind of show how well each pattern matches with the observation. So you can see a lot of these have close to zero values, but these patterns have a higher value because it's kind of matching. Okay? So this is kind of an intuition. And one good thing about this idea is it makes the algorithm and also the prediction very explainable. So it's easy to explain why the algorithm made such and such prediction. Okay, and then one novel idea here was instead of using the traditional convolution operator, Eagle uses something closer to Euclidean distance calculation for the convolution, because the motion pattern matching is more on the distance calculation. So here it's a common example where if you use the traditional convolution operator, given this pattern, this one gets a closer value, which is not what we want. So we want these to become a better match. Right. And then another nice thing about spec is representing the uncertainty in the output space. So a lot of prior approaches use a deterministic prediction, which is just giving one trajectory, one step trajectory output. And the probabilistic output approaches came out, but it was more of a single Gaussian distribution. So the problem is sometimes there are multiple possible ways. For instance, you can avoid an obstacle in front of you by going to the right or the left, but probably more or less equal probabilities. But if you use a single model, then like by choosing just one, it is close to kind of deterministic way. So you either turn right or left. So so this was a kind of limitation of the existing approach. So what Eagle did was using a Gaussian mixture models so that we can predict the multimodal prediction. Okay, so this is the architecture that was used for implementing this idea, and you can see this first part is the agent's own trajectory history. So given the history using this encoder, so inside each encoder there is a motion pattern runner, and then the CNN encoder that's encoding the trajectory input. So this is the trajectory of the agent itself, and then this part is the social part. So encode everyone else's trajectory the same way, and then use the social pooling, which is kind of popular idea that was also used by other people too. And then finally, using bivariate Gaussian mixture model to make the prediction. So this part shows the motion pattern learning. So this illustrates even if we use a very different seed at the beginning, they converge or to very similar pattern to make the predictions. Okay. And then this is again qualitative examples to show. So these the true true value is the dotted line, and the starred path is the prediction. So you can see how well they match. And sometimes you see an example that's kind of diverging, but those diverging examples also kind of make sense because sometimes you see the observation that's actually surprising. So the agent looks like the agent is continuing, but made a sudden turn. So it is a kind of understandable behavior. Okay. So again, according to the popular metrics like the displacement error, so there are two displacement errors commonly used. So the idea is because it's a prediction algorithms, we have a recording of a trajectories, and then use only the up to a certain time step trajectory, and then use those history to make the prediction for the future time steps. And then since it's a recording, you can compare with the ground truth and then measure the distance. So the final displacement error is measured at the goal, like the final step. So it's only checking whether you reach the same goal. Whereas the average displacement error is calculated over the whole entire trajectory. So it is kind of looking at the behavior during the whole run. So those two are the most popular one that's used for trajectory prediction algorithms. So, and then there are some other metrics proposed as well, but not as popular. And the evaluation, the majority of existing work just uses the data sets that are listed here. And then a few existing work actually do the robot testing or use the simulation environment. But these simulation environment, I'm going to revisit like what the problems are there. And for the robot testing, also I have some results to share, but everyone has a different setup. So it is very, very hard to make a kind of side-by-side comparison for this. So evaluation is difficult, but on this existing setup that people have been using, the performance is reaching kind of saturation. So everyone is doing well. And ours is slightly better, then another paper comes out. So it's kind of an incremental improvement, very, very slight changes. but not like the breakthrough. So the question is, it seems like the performance is reaching kind of a plateau, but has the problem solved? Because the answer is not really. So, okay. So that's for the trajectory prediction. And we are going to look at the social navigation part a little bit. Okay, so the social navigation is the navigation problem. So we have a definite goal to reach, but while the agent is heading towards the goal, it wants to be socially compliant. Okay, so under this problem category, there are roughly 3 different approaches. Again, this is very general or very subjective view of you're looking at this field. So the first one is inverse reinforcement learning or learning from demonstration. So intuitively, it is kind of trying to learn from how people navigate. So it is because it's mimicking is the most important objective here is. So the objective kind of matches with the naturalness. So the learned behavior looks very human-like and very much like the data set. But what's missing here is the safety. So there is no explicit way of enforcing collision avoidance. So the algorithms that are using inverse reinforcement learning for this particular problem domain, if we just run this algorithm in a kind of simulation for a longer time, then we do see a lot of collision because there is no sense of like collision avoidance at all. And conversely, the reinforcement learning algorithms are trained using safety as a reinforcement. So if there is a collision during training, there is a penalty. So the reinforcement learning agents learn to behave very, very safely. So the algorithms are under this category can be considered as the most safe algorithm, but it also has the downside because it wants to be safe. So if the population density increases, then the robot usually cannot really find a way because it seems like it's very hard to avoid the collision because there are too many agents or too many people. And also the behavior doesn't look that natural because it's really geared towards safety. Okay. So what Andy, again, one of my students tried was, what about having both? So let's try to have the safety as well as the naturalness. Okay. So this idea is kind of borrowing the theory from psychology or cognitive science idea. So there is a model called the social force model, which is like there is an intention force that it's kind of self-interested, I want to reach my goal kind of force. And then there is a social impact. So I really want to get there, but there are some people, so I don't want to disrupt the crowd. So this is kind of public interested, a little bit of a social aware force. And then there is a obstacle or social interactions, but this part for our purpose, we just simplified this part. And then the natural kind of fluctuation, the stochasticity. I think it's kind of running behind, so I quickly just go over. So this literally kind of it's a computational implementation of the social force model. So there is an intention force, and then the social force, and then the fluctuation and pulling function there. Okay. So So for training the intention force, it makes sense to use the final displacement error, which is measured at the goal locations because intention is to reach the goal. And then for the social part, which is like the whole trajectory, like you want to behave nicely throughout. So it makes sense to use average displacement error as the loss. Okay. And then the third thing was to enforce the safety, the resistance loss was added. And this is the part that we probably can do some more future work to learn how to adjust this social distance. Because for instance, before COVID, it was 0.2, so it's kind of 20 centimeter distance was a socially acceptable distance. But now it has to be kind of 2 meters after COVID. So things like this kind of changes over time and also depending on the social context. And we humans are very good at catching these changing social norms and very, very adaptive to different environment. So how do we design a robot to do the same is a kind of research question. Okay. So this is the architecture. And then this is an example kind of illustrating how this social awareness changes the agent behavior. It's a little bit hard to see, but look at this green one. This is using only intention. And look how close this one gets to this blue one. And on this other side, it's exactly the same scenario. And this one kind of waits for the other agents to go first and then pass. So it kind of shows this very subtle behavior differences. And then for this one, we did like the data set analysis too. But in addition to that, we did the robot experiments and really got a good score. But again, it's very, very hard to sell the story because there is no side-by-side comparison with the other existing approaches. So this is a challenge for the roboticists. Like, how do we come up with a robot evaluation that can be used by many other people as well? So this is a big question. So how, it's more of a question or the quest for this social robot navigation problem or robotics in general as well. Okay. So one approach that I'd like to kind of pitch for was, can we use simulation environment as a little bit better? So in order to really evaluate it, we have to test the robot in a human populated environment, which it has to be carried out, but it is very expensive procedure and it's not really reproducible because people are different and every time when something changes, the behavior is going to be different. It's very difficult. And at the same time, if we have a simulation environment, how do we simulate? That means if we know how to simulate human social, it means we already solved it. So it is kind of chicken and egg. But nevertheless, we still want to use a simulation environment and see if there's something that we can do. So this is kind of different. So this is work by Sam and Advai. So first, what we did was, let's first come up with a set of evaluation metrics in addition to like the ones that are used in the community. How to evaluate the population behavior. So it is more like a traffic or population density, congestion score, and how close the agents get to each other, and whether there was a collision, and so on. So we looked at the existing literature and whether it compiled all the proposed evaluation metrics. And also we included some of our own inventions as well. Okay, So we have a social navigation simulation environment and some set of evaluation metrics. So what kind of research can we do if we have these tools? So the first thing is, since we have these evaluation metrics, to revisit the data sets. So, and evaluate each data set according to these evaluation metrics, so that we can use this as kind of a guidelines. So these will serve as how human work if we generate agent population. Okay. And one finding is the statistics really vary across the different data sets. So this is a kind of an expected result, but at the same time, not really like promising, because it makes it hard to use like one bar to say, oh, this is the human life. So what we can do is each data set has its own characteristics. So for instance, among these popular data sets, university set is the most crowded and also includes a lot of variety options. So we might want to use the statistics from the university set to generate maybe a little bit lively setting. So each data set has different features, characteristics, and then we can maybe base these statistics to create similar simulation environment. So for instance, what we can do is we have several implementation of the current, like the top performing navigation algorithms. And then in self-play settings, so self-play is a setting where everyone is using the same algorithm. So RVO, for instance, is an algorithm. And if we populate like 20 agents and everyone is using the same algorithm, and then kind of try to reach their destination. Okay, so then we can use these evaluation metrics to compare RVO population with one of the existing data set populations. So in this case, we compare that with the university. So like how RVO population behaves according to the metrics, how similar or how dissimilar to the university is. So this is was a kind of interesting experiment. So this is still an ongoing part, but we are getting some interesting numbers here. And again, this was an expected result. So there is no like single algorithm that's a clear winner. So in some cases, this one is closer, and some other cases, the other algorithms. Okay, so this kind of leads to the kind of an idea that we might want to have a mixture of different algorithms to populate an agent population that's similar to a certain human population. Okay? And then another thing that we can also play with is we since it's a simulation environment, we can do a lot of kind of tuning parameter or controlling parameters. So after generating a lot of Asian population, we can play with the population density, for instance. So if you play with the density, this is a kind of example. The linear algorithm is kind of blind agent. So it doesn't even care who else is out there. So it always just goes straight to the goal. So in terms of the arrival rate, they always reach the goal, and they are perfect. But look at the collision rate. It's the worst algorithm because it doesn't look at other agents. So it has a lot of collisions, but it just goes through. So these are not surprising, but we still need to analyze all these algorithms so that we can learn what type of behavior each algorithm kind of mimics in the human population. So other things we can do is kind of a tournament setup so that we can analyze like the behavior characteristics of the algorithms. So Let's just skip through. So this repository with the toolkit, we are going to release it soon. So, okay. So to wrap up the future direction for this the social navigation, there is just a lot of challenges. So today I covered some of the algorithmic or the planning decision-making side challenges using some of the like existing approach that we tried. And then discussed a little bit about the evaluation challenge, like why is it so hard to create a decent evaluation system for really comparing algorithms or comparing different approaches in this particular problem domain. And then things that I didn't really talk too much about is like the perception challenges. So all the algorithms that I discussed today is a trajectory based. So meaning that a pedestrian is represented as a single point in 3D space at a fixed time step. So it doesn't have a notion of a volume or the first person view vision. So the visual context is not used at all. And of course, the environmental context is largely ignored, which I mentioned earlier. And then how to learn these social norms. So right now it is very implicit. We just want to use a lot of data so that the agents can just naturally learn. But are there better ways to model these social norms? And then also from the multi-agents perspective, all the existing work so far, the ones that I discussed today, it's assuming homogeneous agents. So these are either all humans or robots, like a single type. So how do we turn this into a really dynamic environment where there are cyclists, cars, and other things, okay? And then also the other things is in the action space. So when I defined the problem at the beginning, the planning was to take a sequence of actions to reach the goal. But when I discussed all these algorithms, all the algorithms consider only the moving actions. Like I'm gonna go this way type of moving actions. But what about other types of actions like coordination actions, like speaking or saying something like excuse me, that will open up the space. So these are kind of a very, very different way to look at the same problem of using communication to actually make other agents to take different actions. Okay? And then the last one is more human-robot interaction topics like tactile sensing or physical HRI. So if you look at this example of a really packed environment, in order to pass through this type of environment, physical contact is unavoidable. So how do we deal with this? So, and then the last one was the finding from the robot experiments. People tend to react differently according to really based on the appearance of the robot. So that impact was it's kind of like humiliating to be a human moment. So like how come people are so affected by the appearance, even for the robot? So that was kind of an interesting finding. And finally, the majority of the discussion was from the survey article that I wrote with these colleagues. Okay. Some references. And thank you so much for your attention.
네, 아주 흥미로운 발표 잘 들었고요. 시간이 뭐 많지 않아서 한 5분간 Q&A 세션을 진행하겠습니다. 그래서 질문 있으신 분 연사님께 질문을 해주시면 감사하겠습니다. 질문 없으신가요, 아무도?
혹시 다른 질문 없으시면 제가 하나 여쭙고 싶긴 한데요. 오늘 발표 재밌게 잘 들었습니다. 그 전반부에 말씀해 주셨던 이제 페데스트리얼 그 프레딕션 같은 경우에 오늘 말씀해 주신 연구의 방향은 그 프레딕션 에러를 어떻게든 줄여보자 이제 그런 것으로 이해하고 있는데요. 100% 정확한 건 없으니까 이제 뭔가 에러는 발생할 수 있고 그러면 그런 거에 대한 대책은 내비게이션 단에서 처리하는 건지 아무튼 제 질문은 프레딕션이 틀렸을 경우에 대한 그런 대책 같은 경우도 연구가 되고 있나 이런 것 좀 여쭙고 싶습니다.
예, 그러니까 이제 지금 이밸루에이션에서 제가 이제 말씀드린 게 리코딩하고 비교를 해서 딱 매치되는 것을 이제 제일 좋다고 하는데 이제 그것의 문제가 어쩔 때는 보면은 두 개가 아니면 그러니까 여러 개의 옵션이 있을 수 있는데 그 중에서 그 리코딩 된 거는 왼쪽으로 간 것만 있는 거예요. 그러면 사실 오른쪽으로 피해도 되는데 그 오른쪽으로 프리딕션을 할 수도 있잖아요. 사실 왼쪽 오른쪽 똑같으니까. 근데 오른쪽으로 프리딕션을 하면 굉장히 그 페널티를 많이 받는 거예요. 이밸류에이션 받을 때. 그래서 이제 그게 하나의 이제 문제고 그 다음에 프리딕션이 틀렸을 경우는 그러면 이게 계속 sequential decision making이니까 그 다음에 그냥 또 계속 recover하는 또 다른 계속 프리딕션을 만들거든요. 그러니까 한 번 하고 그걸로 계속 간다기보다는 그러니까 그 한 타임 스텝마다 계속 다시 리플레이닝을 하는 거니까 처음에 틀리면 거기에서 이제 그 임팩트가 있잖아요. 처음에 잘못 액션을 했으니까 그러면 거기서 또 리커버를 해야 되는. 예.
네, 아무튼 그렇군요.
네,
그렇게 해서 거기서 커렉션하는 거는 좋겠는데 제 말씀은 그냥 약간 이 연구 전반적으로 시스템 만들려고 하신 거니까 결국 내비게이션 시스템이나 만들려고 하실 거니까 프레딕션 에러가 틀릴 경우에 대한 대책은 그 다음 단에서 하는 건지 아니면 다른 어떤 아이디어가 있는지 그런 걸 좀 여쭙고 싶었습니다.
예, 되게 좋은 질문이고 그다음에 제가 말씀 안 드린 것 중에 이제 이전의 어프로치들은 이 프리딕션을 받은 다음에 리액션을 하는 것으로 플래닝을 했었어요. 그러니까 이렇게 움직이니까 내가 이렇게 하면 옵티멀 액션이 되겠다. 근데 그 모델에서는 그 뭐가 빠졌냐면 그 다른 에이전트들도 이 로봇이나 그러니까 저를 예를 들면 저를 보고 있잖아요. 그러니까
네.
제가 어떻게 움직였느냐에 따라서 달라지는 그게 빠져 있거든요. 그래서 그러면 그거를 집어넣으려고 그러면 내가 이렇게 하면 그러면 이거를 생각하고 그러면 그 인피니트 루프로 들어가잖아요. 그래서 그 다음에 나왔던 이제 트렌드들이 뭐냐면 그 조인트 프리딕션을 하는 거예요. 그래서 다 각자 디시전 메이킹을 하지만 어떻게 보면 이 전체가 같이 움직이는 것이다. 그래서 프리딕션을 할 때 그 자기 자신의 무브에 대한 것도 그 모델 안에 집어넣는 거예요. 예.
네.
그렇게 해서 그래서 그게 이제 조인트 프리딕션 하는 건데 그렇고 그렇게 되면서 이제 조금 약간은 이제 해결이 되는데 그 질문하신 문제는 어려운 것 같아요.
잘 알겠습니다. 감사합니다.
시간이 많이 없어서 다른 질문 있으신 분은 저한테 이메일 보내셔도 되고요.
네네.
토픽이
네. 그래서
어떠셨는지
오늘 일단 첫 번째 세미나는 이곳으로 마무리를 해야 될 것 같습니다. 지금 10시여가지고. 그래서 질문이 추가적으로 더 있으신 분은 아까 말씀하신 대로 연사님께 직접 이메일로 질문을 해주시면 아마 답변을 해주실 것으로 생각하겠습니다.